Hello everyone, myself Nataraj K. I welcome you back to the mathematics class of module number 5. Today I am going to solve problems on variational method. The next topic in module 5 is variational problems. In variational problems, we used to determine the maxima and minima of the given extremals or functionals. Okay, under that, first problem is find the extremal of integral x running from x1 to x2 y dash whole square divided by x cube into dx. This first problem is find the extremal of the functional x running from x1 to x2, that is integral of x running from x1 to x2 y dash whole square divided by x cube into dx. Next, the solution of this problem. First, we shall denote f of x comma y dash, that is equal to y dash whole square divided by x cube. Okay, I am denoting y dash whole square divided by x cube as f of x comma y dash. Next, after that, partially differentiating f with respect to y, that is partial differentiation of f with respect to y. Next, in the right hand side we do not have any function of y, therefore it becomes 0. When you are partially differentiating with respect to y, x and y dash are constant. Next, and dou f by dou y dash, that is partial differentiation of f with respect to y dash. When you are differentiating with respect to y dash, partially x cube is constant. On differentiating this partially, you get 2y dash divided by x cube. 2y dash divided by x cube. Next, by Euler's equation, we have this dou f by dou y minus d by dx of dou f by dou y dash equals 0. Next, substituting all the partial derivative values, that is dou f by dou y value is 0 minus d by dx of dou f by dou y dash is 2y dash divided by x cube equals 0. Next, shifting this to right hand side, the negative sign here becomes positive sign, that is d by dx of 2y dash divided by x cube equals 0. Next, we need to get rid of d by dx. In order to get rid of derivative, we need to integrate with respect to x on both sides. Next step, integrating with respect to x on both sides is integrating, we get 2y dash divided by x cube equals, if you integrate we need to write the constant, that is equal to c1, that is in the right hand side if you integrate 0 with respect to x it becomes 0. Next, plus c1, where c1 is integrational constant. Now solving this for y dash, this y dash equals c1 x cube divided by 2. I am shifting x cube to right hand side, it multiplies with c1, it becomes c1 x cube, shifting 2 to denominator of the right hand side. Since y dash is your first derivative, again integrating with respect to x, we get y here. Next, again integrating with respect to x, we get y dash becomes y, that is equal to c1 by 2 is constant, I am writing that outside. By linearity property, I am writing that outside, c1 by 2. Next, integration of x cube into dx. Since we are integrating another time, I am writing another integration constant, that is plus c2. Next, now c1 by 2, integration of x cube is x power 4 by 4 plus C2. That is y equals C1 by 8 x power 4 plus C2. This can also be rewritten as y equals k into x power 4 plus C2, where k is C1 by 8. Where k is C1 by 8. I am just denoting the constant C1 by 8 to k is the required extremal. Okay, we shall pass on to the next problem. Second one, find the extremal of the functional. Find the extremal of the functional integral of x running from x1 to x2 y square plus y dash whole square plus 2y e power x into dx. Next, solution of this problem. Let f of x comma y dash, just leave the integral and denote all the function as remaining function as f of x comma y dash, that is y square plus y dash whole square plus 2y e power x. Next, partially differentiating f with respect to y. When you are differentiating with f with respect to y, we need to treat x and y dash as constant. That is, you get derivative of y square is 2y. Since y dash is constant, second term becomes 0. In the last term, we have 2y e power x. 2y e power x. On differentiating with respect to y, you get 2 e power x. That is nothing but 2y plus 2 e power x. Next, similarly partially differentiating f with respect to y dash, we get here y square is constant, x is also constant. On differentiating this, first term is constant, it becomes 0. Second term we get as 2y dash. Third term we get 0, since y and x are constant. Therefore, dou f by dou y is 2y dash. Next, by Euler's equation, we have dou f by dou y minus d by dx of dou f by dou y dash equals 0. Next, dou f by dou y is 2y plus 2 e power x minus d by dx of dou f by dou y dash is 2y dash. Here y dash is nothing but first derivative. Just observe here, we can get rid of 2 here. Dividing the entire equation by 2. Dividing by 2, we get, that is y plus e power x minus, here dividing by 2, we get rid of 2. Next, y dash. If you differentiate, y dash is nothing but first derivative. If you differentiate y dash again, we get y double dash. This y double dash equals 0. Now shifting minus y double dash and plus y to the right hand side, it becomes positive sign. That is y double dash minus y equals e power x. I am shifting y double dash and y to the right hand side, it becomes y double dash minus y equals e power x. Now y double dash is your second order derivative. This can be rewritten as d square y by dx square minus y equals e power x. Now in terms of d operator, this can also be rewritten as d square minus 1 into y equals e power x, where d equals d by dx. Next, as usual, this is the differential equation you have already solved in your previous semester. Now first writing auxiliary equation Auxiliary equation is m square minus 1 equals 0. That is, I am replacing d by n, d by m. That is, you get, on solving this, you get m equals plus or minus 1. Therefore, complementary function yc equals c1 e power x plus c2 e power minus x. This is your complementary function. Next, now yp equals, right hand side we have e power x divided by f of d. F of d is d square minus 1. This is of type 1 in your second semester. That is, in order to find the particular integral, this is your old method. That is, this is the type 1. Here coefficient of x is 1. That is, we need to replace d by 1. I am repeating once again. Here coefficient of x is 1. I am replacing d by 1. If you replace d by 1 here, denominator becomes 0. That is, e power x by 0. If denominator becomes 0, you need to multiply by x. You need to multiply by x. That is, x into e power x divided by differentiation of d square minus 1 with respect to d. A simple differentiation. If you differentiate this with respect to d, we get 2d. We get 2d. Again replace d by 1. If you replace again d by 1, therefore yp we get as x e power x by 2. This is your yp. Therefore, complete solution is y equals yc plus yp. Here yc is c1 e power x plus c2 e power minus x, and yp is x e power x divided by 2. This is your y. Is the required extremal. Is the required extremal. This is the second problem. Okay, now we shall pass on to the next problem, that is problem number 3. Find the curve, that is third one. Find the curve on which the functional x running from 0 to 1 y dash whole square plus 12xy into dx with the condition, that is with y of 0 equals 0 and y of 1 equals 1 can be determined. Can be determined. Okay, in your previous two problems, the initial condition has not given, but here in this problem they have given some conditions, that is y of 0 equals 1 and y of 1 equals 1. Next, using this condition, we need to solve this functional, that is x running from 0 to 1 y dash whole square plus 12xy into dx. Y of 0 equals 0 means y value is 0 when x equals 0. Similarly, y of 1 equals 1 means y value equals 1 when x equals 1. Okay, let f of x comma y dash equals y dash whole square plus 12xy. Next, partial differentiation of f with respect to y. Partial differentiation of f with respect to y. Here x and y dash are constant. Y dash is constant, first term becomes 0. In the second term, 12x is constant, derivative of y is 1, you remain with 12x. And partial derivative of f with respect to y dash, that is dou f by dou y dash equals 2y dash plus 12xy. Since x and y are constant, second term becomes 0, you remain with 2y dash. Next, by Euler's equation, we have dou f by dou y minus d by dx of dou f by dou y dash equals 0. This is the expression for Euler's equation. Now, dou f by dou y is 12x minus d by dx of dou f by dou y dash is 2y dash equals 0. Since we have 12 and 2 here, you can divide the entire equation by 2. On dividing by 2, it reduces to 6x minus, here dividing by 2, 2 get cancelled, so you remain with only y dash. If you differentiate y dash again with respect to x, it becomes y double dash, that is y double dash equals 0. Next, y double dash equals 6x. I am shifting minus y double dash to the other side, it becomes plus, that is y double dash equals 6x. This can also be rewritten as d square y by dx square equals 6x. Next, in order to solve this, we need to integrate 2 times. That is, on integrating the order 2 reduces to order 1, that is d square y by dx square. On integrating, it becomes dy by dx equals 6 is constant, integration of x into dx plus c1, that is 6 into integration of x is x square by 2 plus c1. Therefore, we get dy by dx equals, here 2 ones are 2 3s are get cancelled, to get 3x square plus c1. Next, again integrating with respect to x, dy by dx becomes y, dy by dx becomes y, that is 3 is constant, I am writing that outside, x square into dx plus c1 into integration of 1 into dx, again integration constant c2, is you get y equals 3 into integration of x square is x cube by 3, next plus c1 into integration of 1 is x, next plus c2. Here 3 get cancels, therefore y equals x cube plus c1x plus c2. Call this as equation star. Okay, next they have given some conditions. This given y of 0 equals 0. First condition, I am considering the first condition, y of 0 equals 0, that is y value is 0 when x equals 0. Y equals 0 when x equals 0. I am substituting the value of x and y in equation star, that is star becomes y equals 0, left hand side becomes 0, that is equal to first term of RHS also becomes 0, second term of RHS also becomes 0 since x equals 0. Next, you remain with C2. Therefore, the value of C2 is 0. Next, again they have given another condition, that is y of 1 equals 1, that is y equals 1 when x equals 1. Again they have given y of 1 equals 1, that is y equals 1 when x equals 1. Now again substituting these values in equation star, that is star becomes when y equals 1, left hand side becomes 1, that is equal to first term of RHS 1 cube is again 1 plus c1 and the value of c2 is here 0, therefore last term becomes 0. Next, if you shift 1 here, 1 minus 1 becomes 0, therefore value of c1 is also 0. Next, lastly substituting c1 and c2 in equation star, substituting c1 and c2 in star, we get this y equals x cube, c1 is also 0, c2 is also 0, is the required curve. This is your problem number 3. Okay, we shall pass on to the next problem. This is problem number 4. Solve the variational problem x running from 0 to pi by 2 y square minus y dash whole square into dx equals 0, given they have given the condition as y of 0 equals 0 and y of pi by 2 equals 2. Okay, next solution of this problem is let the functional, that is f of x comma y dash equals y square minus y dash whole square. Next, now partially differentiating f with respect to y, that is dou f by dou y equals 2y. Since y dash is constant, on differentiating partially it becomes 0, and dou f by dou y dash, since y is constant, first term becomes 0, dou f by dou y dash is minus 2y dash. By Euler's equation, we have dou f by dou y minus d by dx of dou f by dou y dash equals 0. This is the expression for Euler's equation. Now substituting all the derivative value, is 2y minus d by dx of dou f by dou y dash is minus 2y dash equals 0. Just observe that here coefficient of y is 2 and coefficient of y dash is also 2. We can easily remove 2, or dividing the entire equation by 2, the 2 goes off. That is, dividing by 2, we get this y. Here we have minus, again we have minus into minus, it becomes plus. Y dash is your first derivative, again differentiating with respect to x, it becomes y double dash, that is y double dash equals 0. This can also be rewritten as d square y by dx square plus y equals 0. That is, this is your second order ordinary differential equation. That is, in terms of d operator, this can be rewritten as d square plus 1 into y equals 0, where d is d by dx. Next, solving this, that is auxiliary equation is m square plus 1 equals 0. Finding the roots for m, you get m equals plus r minus I. That is, since right hand side equals 0, yc is your complete solution. That is, yc is your complete solution, that it becomes y equals c1 cos x plus c2 sin x. Call this as equation star. Now they have given the conditions. That is, I am considering the first condition, y of 0 equals 0. Given y of 0 equals 0, that is y equals 0 when x equals 0. Substituting these values of x and y in equation star, that is star becomes when y equals 0, left hand side becomes 0, that is equal to c1 cos x. Here we have cos x, when x equals 0, cos 0 value is 1. Next, plus c2 into sin 0. Next, sin 0 value is 0, you already know that. Therefore, we end up with c1 equals 0. Similarly, we have another condition, that is given y of pi by 2 equals 2. That is, y value equals 2 when x equals pi by 2. Next, again substituting the value of y and x in equation star, we get, that is star becomes here left hand side we have y equals 2, that is 2 equals c1 cos pi by 2. When x equals pi by 2, it becomes cos pi by 2. Cos pi by 2 value is 0. Next, plus c2 into sin x. When x equals pi by 2, it becomes sin pi by 2. Sin pi by 2 value is 1. Therefore, on simplifying this, you get c2 equals 2. Now, at last, substituting the value of c1 and c2 in equation star. Substituting c1 and c2 in star, we get this y equals, since c1 is 0, I am leaving the first term, c2 is 2 sin x is the required extremal. This is your problem number 4. Okay, we shall move on to the next problem. That is number 5. Solve the variational problem x running from 0 to 1, x plus y dash whole square into dx equals 0. Given the conditions as y of 0 equals 1 and y of 1 equals 2. Okay, next solution of this problem is, let f of x comma y dash equals x plus y dash whole square. Next, partially differentiating f with respect to y, that is dou f by dou y equals, since when you are partially differentiating with respect to y, x and y dash are constant, first term becomes 0, second term on differentiating partially it becomes 1, and dou f by dou y dash, that is partial differentiation of f with respect to y dash, when you are differentiating partially with respect to y dash, x and y are constant, that is x is also constant, y is also constant, first two terms become 0, so you remain with 2y dash. Next, by Euler's equation, we have dou f by dou y minus d by dx of dou f by dou y dash equals 0. Now, substituting all the partial derivative values, 1 minus d by dx of dou f by dou y dash is 2y dash equals 0. Next, 1 minus, if you differentiate y dash again with respect to x, it becomes y double dash, that is 1 minus 2y double dash equals 0. Next, solving this for y double dash, that is I am substituting now I am shifting the position of minus 2y double dash to right hand side, it becomes positive, that is it becomes 2y double dash equals 1. On solving this for y double dash, you get y double dash equals 1 by 2, that is y double dash is nothing but d square y by dx square, that is equal to half. Here the order of dy by dx is 2, that is we need to integrate 2 times, that is integrating second order reduces to first order, that is dy by dx equals half is constant, I am writing outside, integration of 1 into dx plus integration constant c1, that is you get dy by dx equals integration of 1 is x plus c1. Next, again integrating with respect to x, we get that is dy by dx becomes y, half is constant, integration of x into dx, again c1 is constant, integration of 1 into dx Next plus, since we are integrating second term, I am writing another constant, that is C2. Is equal to x integration is x square by 2, again one integration is x plus C2. Therefore, we get y as x square by 4 plus C1x plus C2. Call this as equation star. Now, they have given two conditions. Again, given y of 0 equals 1, that is y equals 1 when x equals 0. Substituting the value of x and y in star, that is star becomes y is 1, x is 0, first term becomes 0, second term also becomes 0 plus C2. Since x equals 0, 0 first term becomes 0, second term also becomes 0, you remain with only C2. Therefore, the value of C2 is 1. Similarly, they have given another condition, that is y of 1 equals 2, that is y equals 2 when x equals 1. Again, substituting these values in equation star becomes this 2 equals when y equals 2 and x equals 1, you get 2 equals 1 by 4 plus C1, C2 value is again 1. Next, I am shifting 1 to here, 2 minus 1 becomes 1. Next, again shifting 1 by 4 to left hand side, it becomes minus 1 by 4. In right hand side you have 1, 1 minus 1 by 4 is 3 by 4. Therefore, C1 value is 3 by 4. Next, last step, substituting C1 and C2 in equation star, we get y equals x square by 4 plus 3x by 4 plus 1 is the required extremal of the given problem. Okay, we shall move on to the next problem. It is problem number 6. Find the extremal of the functional x running from 0 to pi y dash whole square minus y square plus 4y cos x into dx. Given y of 0 equals 0 and y of pi is also 0. That is, they have asked to find the extremal of the functional x running from 0 to pi y dash whole square minus y square plus 4y cos x, given the condition as y of 0 equals 0 and y of pi is also 0. Okay, let f of x comma y dash is y dash whole square minus y square plus 4y cos x. Next, partially differentiating f with respect to y, treating x and y dash as constant. Since y dash is constant, first term becomes 0. Next, second term becomes minus 2y plus 4 cos x. And derivative of f with respect to y dash partially, that is, you get 2y dash. By Euler's equation, we have dou f by dou y minus d by dx of dou f by dou y dash equals 0. Substituting the derivative values, we have minus 2y plus 4 cos x minus d by dx of 2y dash equals 0. Just observe that each term has the coefficient 2. In the first term we have 2, in the second term we have 4, and in the last term we have 2. Again we can divide the entire equation by 2. So it becomes minus y plus 2 cos x. Next, derivative of y dash again with respect to x becomes y double dash equals 0. Now we shall shift minus y dash and minus y to the right hand side. Since it has negative sign, if it is shifted to opposite right hand side, it becomes positive sign. That is y double dash plus y equals 2 cos x. Since y dash is nothing but second derivative, I am rewriting this as d square y by dx square plus y equals 2 cos x. Next, in terms of d operator, this can be rewritten as d square plus 1 into y equals 2 cos x, where d is nothing but d by dx. Next, we shall solve this differential equation. Auxiliary equation is m square plus 1 equals 0. Here we get two roots on solving this, that is m equals plus r minus I. Complementary function is c1 cos x plus c2 sin x. Next, we shall find the particular integral, that is yp equals 2 cos x divided by f of d. F of d is d square plus 1. Again this is of type 2 in your previous semester. On solving the differential equation, you have already learnt these types. That is, we need to replace the value of d square as minus 1. Just observe the coefficient of x here. In cos x, coefficient of x is 1. I am writing minus first, and after that square of the coefficient of x, that is minus 1 square, that is nothing but minus 1. If you replace d square by minus 1, it becomes 0. The denominator becomes 0. If the denominator becomes 0, we need to multiply by x, that is x into 2 cos x. If the denominator becomes 0, first we need to multiply by x. After that, we need to differentiate the denominator with respect to d. D square plus 1, if you differentiate that one time, we get 2d plus 0, that is nothing but 2d. Here 2 get cancels. That is equal to x cos x divided by d. Since we need to replace d square, but here we have only d. Next, multiplying and dividing by d. D is nothing but derivative. Here I have written d equals d by dx. Next, derivative of cos x. Derivative of cos x, you get minus sin x. Minus sin x by d square. Again, you need to replace d square value by minus 1. If you replace d square value by minus 1, therefore we get yp as minus by minus it becomes plus, therefore yp is x into sin x. Next, the complete solution is given by y equals yc plus yp. Yc is c1 cos x plus c2 sin x. Next, plus yp is x sin x. X sin x. Next, call this as equation star. They have given the conditions. Given y of 0 equals 0, that is x equals 0 and y equals 0. That means y equals 0 when x equals 0. Now substituting the value of x and y in star, we get y is 0, that is left hand side becomes 0. C1 cos x, since cos 0 is 1, you have C1 here. Sin 0 is 0, second term becomes 0, third term also becomes 0. Therefore, the value of C1 is 0. Again, they have given another condition. Again, they have given y of pi equals 0, that is y equals 0 when x equals pi. That is equation star becomes, substituting this value of x and y in star, that is we have 0 equals cos pi. Cos pi value is minus 1. Next, sin pi value is 0. This second term also becomes 0, third term also becomes 0. Therefore, value of C1 is again 0. Here we have not got the value for C2. Just keep C2 as it is. Now, substituting C1 in star, we get y equals, first term, since C1 is 0, first term vanishes. You remain with C2 sin x plus x sin x. From these two we can take sin x as common. Therefore, y is C2 plus x into sin x is the required extremal. These are some of the problems on variational method in order to find the extremal of the functional. Okay, thank you all.